Alright fellas, so Module 2 is all about trusses, and in this lesson we'll be talking about the two main requirements which are needed before we can start to do equilibrium analyses: stability and determinacy. So the learning objectives are along those lines. First, we'll learn about common types of trusses and their applications. Then we'll learn how to analyze trusses for stability, and finally we'll do a very similar process to look at how to analyze them for static determinacy and indeterminacy. First, let's look at bridge trusses. Now, bridge trusses are composed of two parallel plane trusses, which are the ones on either side. So here I've outlined the right plane truss, and these are held together by bracing. And you can see there's quite a few types of bracing, like sway bracing, lateral top bracing, and portal bracing on the outside. But we won't worry too much about bracing. We'll study really the trusses. And in terms of the trusses, the real terminology that you need to be aware about is the chords. So the bottom chord is the entire bottom section of this plane truss, and the top chord is the entire top section. There are many possible designs for these plane trusses. Some of the most popular ones you can see here, including the Pratt and Howe trusses, which are very similar except for the orientation of their diagonals. So if you observe, the Pratt truss has diagonal members angled out, whereas the Howe truss has the diagonal members angled in. The Warren truss is like a hybrid of the two. It has alternating diagonal members. One good way to remember the Warren truss is that those members form a W, as you can see. Then we have also a few other more types of complex trusses, like the K-truss, which, as the name suggests, forms Ks or backwards Ks, and the Parker truss, which is very similar to a Pratt, except that it has a rounded top chord. The best type of truss for a given application will depend on the design loads for that application, which is something that we'll get into a little bit later. But in general, the ideal truss is one that will distribute member loads evenly throughout the structure. In other words, you won't have concentrated loads at any particular member. Trusses are also very commonly used in roofs, as you can see here. Again, these are very typical plane trusses. So each of these would correspond to a plane truss. And the terminology is quite similar. We have the purlins, which transfer the load of the roof deck to the joints of the truss. We have the top chord of the truss. We have the bottom chord of the truss. And another very important vocabulary word to know is this gusset plate, which is essentially the most common joint we use to join different truss elements together. Common roof trusses are similar. We have, again, Howe trusses, which have the members angled in, and Pratt trusses, which have the diagonal members angled out. We also have fan and fink trusses, which are quite similar. They always have this internal triangle to them. The difference between a fan truss and a fink truss is that the fan has members that fan out from this connection point, whereas the fink truss will have usually members that connect the top chord to some part of the bottom chord or that internal triangle. So you can see that it has multiple members joining those two. In addition to plain trusses, we also have space trusses, or 3D trusses, which are designed to resist loads in all three directions. You'll see them most commonly used in roofs, particularly to provide bending support in both directions. So for example, bending support in this direction and also in that direction. You can also find them in roller coaster tracks, such as this one, where you would obviously expect the track to experience centrifugal forces or other lateral loads. Now, there are 4 key assumptions we make when modeling trusses. The first one is that all members are straight, slender, and most importantly, in uniform tension or compression. That means that the tension, as you can see from the figure, is the same at both ends, and same for the compression. This also means that there is no moment applied to any of these members, right? So we assume that truss members cannot sustain any moment, only tension and compression forces. So they are in effect tensile and compressive members, but not beams. Assumption 2 is that all members are connected only at their ends and form a rigid body. So as you can see here, members are connected at the ends, and in order for this to be a truss, at least a stable truss, these angles need to be preserved. The whole structure needs to act as a rigid body. The third assumption is that all forces act only on the joints of the truss, as you can see from the figure. So a force acting in the middle of a member is not valid. Again, this is related to the first assumption in that applying a load not at a joint would cause the member to bend, and as we established, these members cannot support moments, so that would violate assumption 1. Assumption 4 is that joints are assumed to be smooth pins. So even if we have a gusset plate, which is somewhat of a rigid structure, we still assume that the joints are completely smooth and enable rotation. So there is one central pin here, and all joints are able to rotate around that pin. The reasoning behind this assumption is really that these types of joints specifically are not designed to support moments. So we really don't want to treat them as moment supports or as rigid supports. Now, in order for a truss to be rigid and thus support load, it must fulfill what we call internal stability. If we look at the simplest truss element, which is a triangle, we see that there is no combination of loads that we can apply to get it to change its geometry. That is, there is no way to get the members to rotate around the joints and still preserve the member lengths. On the other hand, if we look at a rectangular element, we see indeed that there are ways to apply loads such that the members will rotate around the joints and still preserve that geometric constraint, which is the member lengths. So we notice that if we apply a lateral load here, we can get it to rotate around its joints, but these member lengths will still be equal. Keep in mind this has nothing to do with the members deforming or failing in any way. It's simply a geometric reconfiguration. So we would call the triangular element an internally stable element, whereas the rectangular element is internally unstable. Now we can build off that principle and create what we call simple trusses, which are simply combinations of stable truss elements. So the triangular element is the most basic simple truss, but we can also create a new simple truss by adding essentially new joints and new members. So I'll add a new joint D, and new members. And as long as we add one new joint and two new members, we'll preserve the simple truss and stability. Keep in mind that simple trusses do not have to be built entirely off of triangles. You just need to fulfill this rule of one new joint for every two members. So here we have a truss at the bottom that's been built in this way, and we can add another new member another new joint F, which we combine with points E and B. Notice that's not a triangle, but this is still a simple truss and thus a stable truss. So for simple trusses, we can formalize this by saying that the number of members, M, is equal to 3, the number of initial members in the triangle, plus 2j minus 3, which is the two new members per new joint rule. Keep in mind the minus 3 here corresponds to the 3 initial joints. And we can simplify that down to 2j minus 3. Now we can also form what we call compound trusses, which are simply connections of two or more simple trusses to form still another rigid body. And in order for a compound truss to be stable, it must be connected by members capable of transmitting at least 3 force components. And these force components must neither be all parallel or all concurrent. In case you don't remember what concurrent means, that is going through the same point. So let's look at 2 examples. Example 1, we have 2 simple trusses which have been joined at point C. Clearly this is not stable because both trusses are able to rotate around point C. So we'd like to add members such that this becomes a stable compound truss. So what we can do, for example, is join points B and D together. That now creates a stable truss because we can also count the joint as a new connection. Okay, so we've in essence created a triangular truss there that is able to provide forces in this direction, F1, another direction, F2, and a third direction, F3, which is in line with the member BD. So those forces are not all parallel, and they're not all going through the same point. So we can be confident that that is indeed a stable compound truss. Now in the case of the second example, we again have 2 simple trusses. This time they're not connected at a joint, so we need to add members to connect these 2 in a stable way. One thing we could do is try, let's say, connecting C and F together and B and D together. But we notice that those are parallel members and thus apply parallel forces. So that alone would not be enough. So we can add another member diagonally. And so in this case we have force 1, force 2, and force 3, which are not all parallel and not all concurrent. So to generalize our rule for internal stability to both simple and compound trusses, we will slightly change our equation from before by making the equal sign a greater than or equal sign to account for potentially adding members in a compound truss setting. Okay? If the number of members is less then 2j minus 3, then the truss is internally unstable. So the number of members must at least be equal to that number. And in addition, we add the criteria that members must be properly arranged. In terms of a simple truss, each joint must be connected to the structure by at least two non-parallel members. Okay, very similar to the rule that we established before. And for a compound truss, we must fulfill that rule about 3 total forces which are neither concurrent nor parallel. Keep in mind that both of these conditions must be met for stability. One alone is not enough. So let's look at 2 examples. In example 1, we have our Pratt truss. So let's try both conditions. First, we try the m greater than or equal to 2j minus 3. So we need to count the number of members that we have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 members. Next, we count the number of joints. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 joints minus 3. That gives us 21, which checks that condition. And we're still not done. We must check to see if the structure is arranged properly. As we can see, it's built entirely off of triangles, which is a good indication that this is indeed a simple truss. And therefore, we fulfill that criteria as well. Every simple truss is indeed arranged properly, and so this is stable. If we look at example 2, let's check the first stability condition first. If we count members, it's essentially the same truss, minus 1 member, so we can safely say that this has 20 members. And the number of joints remains unchanged, so now this condition is not met. 20 is not greater than or equal to 21. And so we failed the first condition. That's already enough to tell us this is unstable. But let's go ahead and do the second condition just to see. So in this case, we would see that we have a compound truss. We have a truss on the left, which is a simple truss, connected to another simple truss. So those may be considered rigid bodies. But then, as we saw before, it's connected by 2 parallel bars, or 2 parallel members. That violates our condition that our forces must be not all parallel and not all concurrent. So we have a compound truss with parallel connections that violates our other rule, so this is unstable. Indeed, if we think about this and we support the left simple truss and apply a load to the right simple truss, then indeed we expect this to rotate around points D, G, B, and E in such a way. If we wanted to prevent this from happening, we could add an additional member, and this would have to be a diagonal member. So we could add a diagonal member in that direction, or to stick with our Pratt design, one in the opposite direction. Okay, so internal stability makes sure that our truss does not fold geometrically. Static determinacy makes sure that we can actually solve for all the member forces using static equilibrium equations. Therefore, its definition: a truss is statically determinate if all the forces in its members, as well as the external reactions, can be determined by using equilibrium equations. So some key words there are the words external reactions. Notice that until this point, stability, we did not care about reactions. For static determinacy, we do care. All right? So in this case, we will care about the number of members, which in this case is 5. We will care about the number of reactions, which for this case is 3. Right? We have a y component for both A and B, as well as an x component for A. And then again, the number of joints, which in this case is 4. What static determinacy entails is that if we blow this truss apart, that we have enough information to solve for all of our unknowns. So what are our unknowns here? Our unknowns are, first of all, the member forces. So force AC, force CD, force BC, force AB, and force DB. So that is equal to our number of members, so M. And we have to add to that also our unknown reaction forces. So AX, AY, and BY. So that is 5 plus 3 equal to 8. And our number of equations available are the equilibrium equations per joint. And how many equilibrium equations per joint do we have? Well, because joints cannot support moments, then we have only balance of forces. So we have 2 equilibrium equations per joint. So 2J, or in this case, 8. So this is indeed a statically determinate truss because we have an equal number of unknowns and of equations. So now let's formalize this. The truss is statically determinate if we have the same number of unknowns and equations. And like I said, we have 2 independent equations per joint. Now there's a very important note here which says that the 3 equilibrium equations for the entire truss structure are not independent of the equilibrium equations in the individual joints. That means that by virtue of having all your joints in equilibrium, that implies that your structure is in equilibrium, right? So they're not independent conditions. If your joints aren't moving, then your structure as a whole isn't moving either. All right, so writing it in equation form, our condition for a statically determinate truss is M plus R equal to 2J. Okay, so now we can generalize everything we've learned so far, and this is really the most important part of this lesson because it ties together everything we've covered. There are 3 possible cases for a truss. The first is that it's properly arranged and M plus R is equal to 2J. This means that we have the same number of equations as unknowns, and so our structure is statically determinate, and if it's statically determinate, then by default it is stable. Okay? The second case is that it is properly arranged, but M plus R is greater than 2J. In this case, we have more unknowns than independent equations, and therefore our structure is statically indeterminate. That still means it's stable, but it means that we can't solve it using equilibrium alone, and that's something that we'll get to at the very end of this class. The degree of indeterminacy is how many unknowns you have left to solve for. We call that IE, and it's simply the difference between your total number of unknowns and independent equations. In other words, M plus R minus 2J. Oh, look at that. It's over here. Okay, and the third case is where the number of unknowns is less than the number of equations. That indicates that we have an unstable structure. And this could be either due to internal stability, which we discussed, where it's not properly arranged, or external stability, which we haven't discussed, but would essentially mean that it is not properly supported or not properly connected. So if you have only two reactions, that would, for example, give you a statically unstable structure. Okay? So this is really your go-to slide from this lesson, where all the information is condensed in a nice little set of equations. So in summary, we have learned that trusses are very common structures in civil engineering, particularly in roofing supports and bridges, and also stadiums, which I didn't give you an example of, but we'll throw it in there. And then we learned that internal stability will depend only on the geometry of the structure, so the joints and the members. And then static determinacy depends on joints and members, but it also depends on reactions. In other words, is the structure supported correctly as well?